we are here to tell you about what we did for the past 6 weeks working with you guys in your labs.
Yeah, and all right, well, my name is Teddy Nee. I'm from Barrington, Rhode Island, and I'm interning through the Boston University RISE program, and I'm entering my senior year in high school.
I'm Ripple. I am interning through Discovery Internships program. I just graduated high school and I'm going to be a freshman at the University of Waterloo this September.
Oh, nice. So what did we do this summer? Well, so imagine this first of all. So imagine we have a lost traveler with the radio, and he's stuck in treacherous terrain, and so a ground search party is not viable. Well, thanks to technology, we can send this guy right here, a drone, to help search for him. The drone is equipped with a detection system that can tell how strong the radio signal is. So how do we find the traveler only given the radio signal or the strength of the radio signal? So we put this scenario into a very basic scenario where we have a target which is represented by the blue square, and the drone which is represented by the rectangle in the top corner. So we have a drone that's searching for a target. And as you can see by the graph right there, or the picture right there, hotter colors are more likely to appear near the target, and colder colors, which are like the blue colors, are more likely to appear farther from the target. So you can think of this as a heat map, and it is the drone's objective using the information that it gets from the heat map to find the target. This is a classic POMDP because the drone does not know exactly where the target is at any times, and it is always in a state of uncertainty. So this is a quick overview of the process that the drone goes through. Initially, it first reads a state, which is going to be the colors in our case. It then calculates a belief state using the state that it just received. It then implements a control policy so that it determines the best move for it to take. And finally, it makes a move, and it repeats through that cycle.
So my project focused on working in the read state, and for the drone to actually detect the environment, we thought of using visual sensors. And when I first started reading that book, I was kind of shocked because I flipped to the page and they said, like, computer vision doesn't really detect colors. For computers, all that colors are is just a bunch of numbers. And what I had to do was calibrate colors and tell the computer that, hey, this code that you see right here is actually a color. This can be used in identifying the environment you're trying to work in. So the end result of my project focused on finding the location and location of the target and differentiating them using the specific colors. So the overview of my algorithm, it started off with capturing the images by hovering the drone around the environment. And then we would define target conditions, such as the number of colors that would be used in the target, the average variances you allow for this. Then you'd calibrate the colors and make sure you have this basic background to rely on when you actually want to start working to find the target. You convert filters, you draw contours to specify the target. We'll get to that. Pinpoint centroids, match the centroid color channels to detect the target. And so for color calibration, what we wanted to do was convert this image, the original image, into something like this using a YUV filter. Now, the reason we wanted to...
Ripple, can I interrupt you? Why do you want to make that conversion?
Yeah.
The conversion on the previous slide, why do you want to make that?
We want to do that because it's more easier for the drones to actually identify colors when you remove all the other noises from the environment. So we were going to use an RGB filter, but what we thought was, hey, we have 3 color channels to deal with, but when we have the YUV, we have only 2, the U and V. Y would just be the intensity of what you'd be dealing with. So that's why it's more preferable to use a YUV filter.
What does YUV stand for?
It's Yuma, and then that just means, like, Luma means brightness, and then that's what they use for Y, and then U and V are just color chrominance.
Okay, thanks.
So how we start calibrating would be by pinpointing the colors we wanted, and then we'd have to figure out the variances, because not always will all your images be perfect, because what you see here is there's a shadow over this area, and then there's just a lighter, there's more light around this area. So though this is still a red color, the computer can't identify all this as one color. So you wanted to place variances in there. And after we went through the variance algorithm, what we came up with was, suppose I selected this as my first color. Now, this would give me the amount of red pixels in there, the green pixels, blue pixels, and then the amount of variances I could tolerate, and tell the robot that, hey, if it still fits in this range, you're probably very close to that color still, the target color. Next, we wanted to convert this into a threshold. Now, to do this, we could use binary imaging techniques, and this is just better. This is just better when you want to go to contour stage. Now, when you think of threshold and stuff, what's going to happen is you're going to pinpoint one color out, and you're just going to play around with this intensities of that color. So it's kind of like when you have like this nice, beautiful image of a lake and mountains and stuff, and you only want to see that water in the lake, and you just want like that blue color in there. So you're going to black everything out and only have anything that's that's related with the color blue there. So you're just singling out colors. And then after creating binary images, because in binary you only have two colors left then, you could create something like this that gives you a thresholded image, and then that's just easier to map contours out later on. You have to be very careful with all the calibration you do in the beginning, because what I did here was I wasn't careful in pinpointing my points right. So when I had to select my variances and stuff, and therefore the computer actually did not pick up on all of these boxes right here. So it's kind of, the first stage is you kind of have to be very careful. For contours, once you have your contours done, you actually can make boxes around the specific color. So what this used to be initially was the yellow tiles, and now we just have them singled out in one area. And then we have the other colors singled out. And this is really good, because now we could actually just highlight the target block you wanted. See, we had that initially start off with, then that, and now you're just narrowing it down to that. So after you've traced the specific target, you could actually use the area inside a contour and then just find the dimensions. And then using these dimensions, you can actually find the locations, and that's what we're aiming to do. Okay, so that slide just explained that. It's kind of like contour inception. When you go in, there are like a bunch of more matrices in there. And all I did was I found the mean values of all the lengths and dimensions there. And with that, I got this average mean value I could use for one contour. And then with those points, I could actually pinpoint, accentuate it out.
Teddy, can you go to the computer? Maybe you can hit the escape button or something so her mouse works.
And another good technique you want to think about is finding the good contours, because sometimes you don't actually have these perfect boxes to rely on, and that would just mess your calculations up. So therefore, you want to do something where you find just the good areas. So you'd set this fixed value and say, if the area in this specific box is actually higher than that fixed value, this is something I'd actually be looking for. Or if it's like two parallel lines with the same length and stuff, you're probably sure it's going to create a box, and that's how you can make sure that, hey, you're kind of working with the good contours. So this was a very useful vector. What this vector did was all the dimensions we got off for the contours, now we actually have them listed out. So for the first contour, we know that it's placed here on the X scale, the Y scale, and then that's the color it was singled out from during the contour process. So now we kind of have an idea of the centroid points and the colors, but we're not sure of the locations yet. We'll come back to this later on.
Might be too far away from the computer.
Okay, so with those dimensions, we actually figured out the centroids, which is pretty cool because they're actually around just right in the center of each box. And now you're kind of having the computer analyze where exactly you want to go about with this.
So you need to centralize because you want the quadrotor to go on top of the
On top of that.
much as possible on the center.
Okay, thank you. So after we've got contours for all these boxes right here, we actually want to go down to that one blue box we're actually searching for, and that means we'll just have to find that center of this blue box. And to do that, what we did was, hey, we know the distances. We know the distances of these contours from each other, and then we have this fixed center around here that's estimated. So what you could do is you could run this code and say that every time you get a shorter distance, you overwrite the previous shorter distance, and the contour, the centroid with that shortest distance would obviously be your center point. And that's how you locate that center point. And similarly, you could, once you have that center point, you could run a code just like that and figure out where your location for that topmost box is going to be, or where that lower left box is going to be. And that's how you can find the locations of these contours. Now, once we have the locations figured out, we have something called a BG array. So that's just the location of those centroid points, and you've kind of figured out where their locations are. Okay, that's that center point, that's that upper right point and stuff. Now you remember that A vector we made earlier, which had the estimated dimensions and then the color that they extracted out of. We could actually match them up now and then figure out which color it corresponds to. So we're going to use this for now. So we know that it's 501, and the closest one on this list would be that one. And then, once again, this is the closest you get for the Y value there. So that means that the color for the rightmost block there has to be the second color we entered there. So now we found the positions, we found the colors that actually are related with these positions, and this is just a written sentence of telling you exactly what the first color was or second color was. It's pretty cool because it actually works out and shows you the exact colors and positions. So the leftmost is number 4, and that would be red, and it works. So this is how I developed the algorithm with the help of Eric, and detected the location and color of the target.
Yeah, so before I go on, I just want to make sure that everyone's like clear with like what the problem is, and like, so does anyone have like any questions? I'm like, yeah.
Do you only try to identify boxes?
Boxes, for now, that's just our target object. Boxes are the target objects.
Okay, so you could potentially do this for any type of
Yes.
shape. Does it has to be convex?
I think the program I wrote is kind of set to find the maximums and minimums according to shapes that are closer to the boxes and squares. So that's why for now I don't think all the convex shapes, all convex shapes, could actually work for this.
Second question. In the beginning you do color calibration. That means that you assume colors don't shift over time. So basically like for an indoor environment, not an outdoor environment, right?
Yeah. So you do color calibration before the experiment usually, and then you assume they stay constant, because otherwise, it's a really hard problem.
I have a question. So when you calibrate your colors, so how many images did you use? Just one or?
Just one image.
Just one. But when the coordinators move around the environment, if you see the color from different angles, the color may change a little bit, I think. Is that true?
Yeah, so that's what we took into consideration when figuring out the variances. Because the color can change, and it can't, though it's one fixed color you see, and there could be different shades of that color, you have something called variances where if it fits that range, it's still going to be considered that color.
So how did you come up with those variances? Did you look at colors from different angles and stuff like this, or?
I made this algorithm in which I got the maximums and minimums of pixels, the color pixels we're looking at, and then later on I pinpointed other shades that were closer to that, and I just subtracted the differences I get. So that would be my range. And I said if it fits in this range, we'll assume that it's this color.
But in principle, you can do what he suggested. Look at different from different distances, different angles, and then come up with variances based on that. It should be easy, right? You're just going to change the variances.
Yes.
Okay.
All right. So, well, now that we have the color, well, we need to. Well, what are we going to do with this color? Because that doesn't really tell us how we're going to find the target. So, in order to find the target, we're going to need to generate a belief state of where the drone believes the target is. So a belief state is just a matrix of probabilities of where the drone believes the target is. Now, in order to find the belief state, we implemented a Bayes filter, which this Bayes filter will help us consider not only the current observation of the color, but also all the previous observations. So for example, if we're above a green color, just this one green color won't really help us determine a good idea of where the target is. If we consider, however, all the previous observations that the drone made, we'll get a much better idea. And this Bayes filter will help us to do that. So this is the mathematical representation of a Bayes filter. So in English, it calculates a belief state using measurement and control data. And in our case, the measurement data would be the color that the drone reads, and the control data would be the probabilities that the color appears given a certain distance away from the target. So right now I'm going to go over the basic logic of how we calculated this belief state. So essentially we went through each tile on the grid and calculated its respective belief. So for example, if we look at this grid right here, we can see that for the next time step, the belief that it has that the target is in this square is going to, so the target has a certain probability of moving into this square given that the drone believes it's in that square. So we can represent the probability that the target moves each tick. We can represent that using delta. So we can see that the target has a delta probability of moving into the square from each of its surrounding squares. And we also have to remember that the target has a 1 minus delta probability of staying in the same square. So if we sum the belief that the target will move into this respective square and the probability that it will stay in that respective square, we can find the belief that the target is in this square. And if we put that into algorithm form, well, first, this is the notation that I'll be using. So given an environment, G made of vectors and edges, or vertices and edges, Y is a set of all the possible observations of the colors. Rho, the drone's current location. Sigma, the target's current location. And the two functions I have defined here is D, given the input, it just returns the distance. And the possible moves function returns a vector of all the given locations' possible movements.
So is that distance measured some sort of a topology of the grid, or is it Euclidean?
It's just the direct distance using this
Direct
diagram theory, yeah. So this is the algorithm that I use. Basically, it just does what I previously said into code form. It just goes through each of the grid tiles and calculates the belief state in respect to the tiles around it. So after it calculates the belief state, it needs to make a decision of where to move using this belief state. So that's why we implemented a control policy, which will determine the best move for the drone. Now we implemented a very basic control policy for now. The priority that it follows, it first looks at the direction to move in. So essentially right now what we have is that the drone, it'll only move in the direction that will put it closer to the target, rather than, say, moving away to get a higher belief. The belief will come second. So for example, if the drone can move up or right and still get the same distance away from the target, then I'll consider which move will give it the highest belief. We also implemented different intelligence levels, or in other words, a more advanced control policy. So the few that we looked at were random movements and thinking ahead steps. So the random movement, it's very self-explanatory. It just randomly picks a direction and moves in that direction. And the 1, 2, and 3 move think aheads are also very self-explanatory. It looks ahead in 1, 2, or 3 moves, and I'll explain that a little bit more in depth here. So essentially, thinking ahead, it looks at the current state it has. So for example, we'll say it sees green right now. And right now it has 4 possible actions. It can either move up, right, down, or left. So for each of these moves has a certain probability of happening. And for each of these possible moves, 4 possible observations can happen. It can either be blue or it can be the other 3. So from these observations, each of these observations has a certain probability of occurring. So for example, if the drone believes that the target is below it, then maybe a cold color like blue has a higher probability of appearing above it, since the cold color will appear farther away. And now using this, we can help make the drone pick a better decision to move to. So for example, if we know that yellow has a higher probability of appearing if we move to the right, then we might want to move to the right, since yellow is a hot color, and therefore the drone will be closer to the target. Now this is a simple 1 move look ahead, since it only looks ahead 1 layer, and we can see that it's pretty basic. It only has 16 possibilities. But if we consider another step ahead, we can see how quickly the possibilities grow. So, and then that's only 2 looks ahead, and then if we do another 3, it'll grow even exponentially. And the time it takes for the calculation to occur also increases exponentially. So this is a graph of the amount of moves it took over 100 trials. As we can see, as the intelligence level increases, the amount of moves it takes decreases. But also at the same time, the amount of time it takes for the algorithm to make a move also increases. So for example, 3 move think ahead would take around 20 seconds to make a decision, while on the other hand, random would take almost instantaneous to make a decision. So right here, I made a little GIF of like an example simulation. This is 2 move think ahead. And
can you remind us that the target is blue and your agent is the square?
Yeah. It does take drone a little bit long to find the target since it's only a 2 move look ahead. But as we can see, like, it does narrow down and it does appear to locate the drone or the target eventually. And the next simulation is a 3 move think ahead, and we can see that it finds or locates the whereabouts of the target much faster.
What's the logic of the changing environment?
Oh, it's based on a set of probabilities. So for example, each time set, the grid just regenerates randomly based on, like, for example, this square is really far away from the blue or the target, so it has a certain probability of being a certain color.
Okay.
So technically speaking, like, there's a very low probability that the entire square will be like 1 color, for example, but it's very low. So we did conduct a few live experiments, and we do have a video.
And did you see like how big was the difference in the computation time when you go from 2-step look ahead to 3-step?
2-step took around 5 seconds, I believe. So it's a very exponential growth. So like 1 move took about, I think, 1 second. So it went from like 1, 5, and 20. So it's a very exponential growth. And this is a video of a live experiment that we ran. Oh, it's not showing.
Try that. Different windows. Mirror the screen or something?
They try that as it works.
No?
Yeah, it doesn't work. I see.
And the graphic is for them. Is this real time, Teddy, or it's
Yeah, it's real time.
Real time.
Is it synchronous? So basically, is the environment changing when? Well,
So basically, every time like the drone makes a move, the environment changes with it.
okay.
And the colors on the ground represent the belief of the drone or
It
the
represents-
sensing uncertainty? Do you
So
know what I
basically,
mean by that?
the colors on the ground are randomly generated based on like the distance from the target, so the drone can get some information of where like the target is.
Okay, so it's kind of like the simulating the sensor of the drone.
Yeah.
And then Ripple, your vision happens on top of this. So you take the image and then you find the different blocks and you look at the colors. Is that happening in that video too?
Not in this one for now, but that's.
That will be
test that.
put in together. Okay, I see. That's interesting.
And so from here, different possibilities include adding more drones. So for example, flying 3 drones instead of 1 drone, which would add more observations and therefore a different algorithm to calculate beliefs. Also, we could implement a more advanced control policy because right now ours is pretty basic. Also, we could add obstacles or restrictions, for example, like walls or something that would restrict the movement.
We actually had such a great summer working here with you guys. It's kind of different than staying at home and watching TV with my other high school friends. But it was
Nothing wrong
great
with that.
learning.
Yeah, that's fun.
Initially, it was kind of frustrating, but you always had your lab colleagues like help you out and tell you you're fine. It's gonna be all right. And just thank you so much for this incredible summer. Thank you, Professor Belta, for having us. Thank you, Kevin, for being such an amazing supervisor. And Eric, thank you so much for just being there and guiding me through all this vision stuff.
Yeah, like, thank you everyone for making this such a phenomenal experience. Like, I never thought like being in the lab, being part of the lab would be so amazing and fun, I guess. And thank you, Professor Belta, for giving this opportunity to me. Thank you, Kevin, for like overseeing, like answering my numerous questions and everything. And thank you, Eric and Ripple, for working on this project with me. It's been a pleasure. And thank you to everyone for just making this such a wonderful culture and environment to work in. So,
Thank
yeah.
you.
Right, thank you guys.